This is a bonus video, and I hope you're interested enough in math to sit through it, because I plan on bringing up some, I think, some very interesting ideas, some of which may be a little mind-boggling when you think about them. One of the aspects of mathematics that has always bedeviled mathematicians through the centuries is the notion of infinity or infinitesimal. And some strange things can happen when you get into this area. And I would say that infinity was not well understood, at least in a mathematical context, until perhaps the middle 1800s. And even the later 1800s, several people, in particular one was Georg Cantor, German mathematician, really explored the notion of infinity and realized there were different sizes of infinities. And so it gets kind of deep, mind-boggling at that level. That I'm going to keep it fairly simple here, but I hope you find this pretty interesting and so forth. All right, so let me throw something at you. Here's an interval which runs from 0 to 2, and it's a let's see, it's an open interval. Let's say it's a half open interval. All right, so it's closed at this end, but it's open at that end and shaded in between. So this would represent an inequality notation, or I'm sorry, an interval notation. X belongs to the interval from 0 to 2. And then here's an interval which runs from 0 to 1, and it's a closed interval of numbers in between, and we'd say X belongs to the interval from 0 to 1 inclusive. So here we have a half open interval, here we have a closed interval, and what's kind of, I think, interesting about this is we can make an argument that this interval is larger than that interval. All right, now you're going to see the distinction is it's kind of moot ultimately, but which interval contains more numbers? You think, well, gosh, this one contains about twice as many numbers, doesn't it? Oh, not really. This interval contains one more number than that interval. And how in the world can that be? Well, the secret to this is to set up a one-to-one correspondence. And by that I mean, okay, I'll give you some examples. Suppose I take the number 0 and I pair it up with 0 up here. So those two numbers match up. Here, let's take the number 1/2 and I'll pair it to the number 1 over here. Here I'll take 3/4 and I'll pair it with 1 1/2 over here, or 3/2. And one more. I'll do 1/4 and we'll pair it with 1/2. Alright, so we can find a way to link each number in this interval with every number up there. And how do you do that? Well, if you give me a number on this number line, if I multiply it by 2, then I get a corresponding number up here. But if you give me any number up here, and if I divide it by 2, then I can match it with a unique number down here. So you can find a comparison, a mapping we call it, or one-to-one correspondence between all the numbers in this interval and all the numbers up there. So they had the same number of numbers, except for this one. This number has nowhere to go to. And so this short interval has one more number than the longer half-open interval. All right, so that seems a little crazy. And in fact it is, because sort of the fallacy into thinking is that both have an infinite number of points, and so really they're on the same size. They both have an infinite number of points. But even at that, it's kind of interesting because this seems to be twice as big as that, but they contain the same number of points because of the way we can link them, except for this exceptional point 1. So that's one kind of weird thing there, and that tied in with these inequalities and intervals and so forth. Let me throw another one at you, and what is, I love this question, what is the largest number that is less than 1? All right, so I have a number line, and here's 1. And I'm looking at this inequality. So you could say, well, x is less than 1, or with interval notation, x belongs to the interval from -infinity up to 1, but not including 1. So the question is, what is the largest number in this set? Or what is the largest number that is less than 1? And you say, well, let's see, would it be 0.9999999? Well, how far do you go? How many 9s do you put? We say, well, because if you stop somewhere, then I could always add another 9 on, couldn't I? And so what if we say, well, okay, here's the largest number, less than 1. It's an infinite string of 9s. All those 9s go on forever. And I say, well, but that's not right, because this is equal to 1. You might think, no, that's crazy. They can't be equal. This is a string of 9s. It goes on forever. It never ends. And if you did stop, again, if you did stop somewhere, you could always put more 9s on and make it even larger. So how in the world can they be equal? Well, let me make a case for that. And so let's see. I think you'll agree that 1/3 in decimal form is 0.333333, and that goes on forever. It's an infinite string of 3s. And you'll probably see where this is heading. For example, if I looked at 2/3, that's one way I could look at it. That's a string of 6s that go on forever. And I haven't found anybody who will dispute with me that these are not equal. They are equal. And because the fraction creates a pattern, an infinite pattern in the decimals. But if we add these, 1/3 plus 2/3 is 1, and if we add these, we get that infinite string of 9s. So there's a case for 1 equal to that long string of 9s. All right. So now, if you're still uneasy about that, say, well, I don't know, this is weird, but I still don't think they're the same. Well, if they're not the same, then two numbers are not the same. There must be one in between, right? And what could possibly fit between an infinite string of 9s and the number 1? So, okay, that's great. So suppose you buy this, and you should, because it's absolutely true. Okay, suppose you buy this, and it's true. What is the largest number less than 1 then? Well, it can't be this number, can it? Well, then there must be something a little bit smaller, right? Maybe there's one that has an 8 somewhere. All right. Well, if there's an 8 somewhere, then I could change that 8 to a 9, and change the 9 over here to an 8, and create a larger number. That's still not the same as this. And so no matter what you try, you cannot find a number that doesn't equal this. That is the largest possible number. There is no largest possible number less than 1 that we could possibly write down. So there's something to think about. How can there be a number, a largest number less than 1? Well, we could speak in the abstract about that number, but I don't know if we could actually make any kind of sense of it. So the answer is, what's the largest number less than 1? I would have to say there is no such number. Largest number less than 1. Certainly not one we can identify. All right, so there's some more fun with infinity and intervals.